Hello and welcome to the Geotechnical Labs in DKIT, and we're about to start the first of our soil mechanics laboratory experiments. And this experiment is the classification of soils using the Atterberg limits, or to give them their full name, the liquid and plastic limits of the soil. So today we're going to be testing a clay type of soil, and the Atterberg limit test helps us to tell whether a soil is a clay or possibly a silt, and we'll see how to do that later in the tutorial part of the lab session. So let's take a look at the soil we're going to test and what we mean by the terms plasticity and liquidity. So I have a sample of soil here in front of me, and as you can see, this material here is very much a clay. It's a brown clay. If I roll it, I can easily change its shape into any other shape, and it holds that shape. If you can squeeze soil and change its shape and it doesn't bounce back to its original shape, we call that property its plasticity. And plasticity is closely related to moisture content. As the soil gets drier, it starts to lose its plasticity, and eventually the water content of the soil, when it gets low enough, reaches a point where the soil ceases to be plastic and starts behaving as an elastic solid. It starts to crack, in other words. And we'll see that later when we do the plastic limit test. But what about the liquid limit? Well, we can see that the soil is kind of wet and soft, and but it's a solid material. It's still a solid material. When we're talking about liquid limit, imagine this soil getting wetter and wetter till it reaches a point where it's behaving like a liquid, effectively like mud. That point of water content, and it could be 10%, 20%, 30% water content, and sometimes higher, that water content is called a liquid limit. It just changes over from being a plastic solid to being a wettish liquid. But how do we measure that? Well, there's a couple of ways of doing it, and we're going to use the cone penetrometer test, which I've set up here beside me. So this is our cone penetrometer, and down at the bottom here you can see a steel cone that we're going to drop into the sample of soil in a moment, and it's attached to a dial gauge. This dial gauge measures the penetration, how far that cone goes into the soil, and it measures it in decimillimeters, or tenths of a millimeter. And it's got a weight on it. The weight here is 100 grams, and to do the test correctly, we time it, and it should take 5 seconds. It's allowed to push the cone into the soil for 5 seconds. So I have an electronic timer here. Electric timer is set to 5 seconds, and this is attached then to a magnet inside in the frame of the penetrometer, and it will drop the cone into the soil and hold it after 5 seconds. Let it sink for 5 seconds. I've taken some of the soil I've just showed you and put it into a cone penetration test cylinder. So I've been careful, I've packed it out fully. You can see I've leveled the surface of the soil so it's smooth and level, and there's no air voids underneath. I've filled out all the voids inside in the sample. I'll put this under the cone, and you can do this test usually about 3 times around a sample. I'll just first of all carefully lower the cone by hand till it's just tipping the surface. Now it's just scratching the surface. But you can see I've created a gap here with the decimeter here, so let's turn that down. And I've also just set it up to 0 at the top. And that's it, ready to go. I could set it off by pressing the button here and holding it for 5 seconds. I'm not going to do that. I'm just going to time it on the timer here. So off we go. And now the cone is sinking into the soil. The question is, how far has it gone in 5 seconds? And you can see here how far it's gone. It's the gap, that gap there. We need to measure that precisely. Let's see how to do that. If we turn the dial gauge, it will bring the cone down. Let's do that. So you can see not the cone roller, but the hammer down. And I've just closed the gap there. And now it's reading off just under 100. In fact, that's about 96 decimillimeters. Now 96 decimillimeters would be 9.6 millimeters. So this sample here has a penetration of 9.6 millimeters. And I would then normally repeat it 2 or 3 times on the same sample to be sure of getting an accurate reading. I mentioned at the start that the liquid limit and the plastic limit of soil are really very closely linked to the water content. So once we have recorded the penetration on the penetrometer here, we need to retrieve the sample. So I'm just going to turn the penetrometer up here, pull out the comb again. You can see the hole where it's been pierced by the comb. And then I'll take a moisture content container. This one has been weighed already, so I know the empty weight of the container. And now I want to know the moisture content of the soil I've just tested. So I'll take a sample of the soil. About 50 grams would be enough, and that would look like this. That's plenty. Pop it into the container. I'll weigh that. Then I'll put it into a drying oven, and the drying oven should be at 105 degrees centigrade, and I'll dry it for 24 hours. I'll take it out of the oven. It will have lost weight, the moisture will have evaporated, and I'll weigh it again. And the change in weight, the drop in weight, is the amount of moisture in our sample, and I divide that by the dry weight of the soil to get the water content of our first test. Now, doing one test on its own is no good, because this particular sample is definitely not at the liquid limit. It's quite firm. And next step is to take our sample material, and I can wet it. I have a water bottle here. Wet a large volume of material. I'm not going to do a large volume now to make it softer. And once I've added some extra water and softened the material, it will get closer to the liquid limit. And then I'll put it back into a penetration test tin and test it again in the penetrometer. And because it's softer, the comb penetrometer here will sink further into it. I'll get a higher penetration, maybe 15 millimeters this time. And then I'll do a moisture content test again on the second sample. And I'll repeat that 2 more times for a total of 4 tests. Now, behind us here, and I'm going to just turn the camera a bit closer here into the sample you can see on the board. I've put up a graph, which is the penetration test result graph, and on the x-axis here is the moisture content. So you can see I have 1, 2, 3, 4 test samples on the graph, and they form approximately a straight line. And in each case, the moisture content has been measured in the way I described, and the penetration here in millimeters is marked on the y-axis. And each of the 4 samples is graphed, and a best fit straight line is placed to join them together. And where that line crosses the 20 millimeter penetration line here, we read off the water content. So it's the water content corresponding to 20 millimeters of penetration is the equivalent to the liquid limit. In this example here, you might not be able to see it, it's approximately 85% water content. That would be very, very high, I must say. So that's what we're going to do in our test. We're going to look at the 3 test samples. Sorry, I should say, we're going to look at 4 test samples, measure the moisture content by drying the sample overnight, and then graph it on the graph I've just shown you to measure the liquid limit. That's the first part of the experiment. The second thing we have to do is to measure the plastic limit of the soil. Remember at the start I said the plastic limit is where the soil goes from being a plastic solid that we can squeeze and change shape very easily, and it holds the shape that we change it into, to being a drier, brittle material. And just where it changes over and starts to crack is called the plastic limit. And this is also a moisture content test, so we'll be taking a moisture content container at the end and taking our samples and carrying out a plastic limit test. So let's have a look at how to do a plastic limit test. Going back here. So for the plastic limit test, what I'm doing here is taking a sample of the soil, and I have a glass plate here, and what I want to do is dry the sample down to its plastic limit, and I can do that using the heat of my hands. I'm just rolling it here as a thread, and in fact we can get a bit more control over it by rolling it on the glass plate. And as I do that, it gets drier and drier. Literally my hands, the heat of my hands is drying it out. When it gets a bit too thin, we can just reform it, and as long as it's above the plastic limit, it will still form back into a plastic solid. It will be easy to change its shape. It's just starting to break up, and the point when it reaches the plastic limit, it becomes impossible to roll it anymore as a thread. I can tell it's pretty much at the plastic limit now. There's very small cracks appearing across the sample. And you can see there just now, I hope you can see on the camera, but it is really starting to crack up. That is literally exactly just now reaching the plastic limit. I've done that by drying it out by the heat of my hands and by rolling it on the glass. So we've been taking moisture out of it, and now it will no longer, if possible, to change its shape plastic. It will just crack up. I hope you can see that on the camera. So what I do is repeat this, and again take a moisture content container which has been weighed empty in advance. I'll take any sample that has reached the plastic limit and drop it in, and then I'll repeat that until I have a reasonable size of sample. I'll keep going, and eventually then I'll have a big enough sample. I'll pop it into the drying oven for 24 hours at 105 degrees centigrade and measure the moisture content tomorrow after the 24 hours. So what we're going to do next is to to process the results from the Atterberg limit tests, the liquid limit tests, which we did here with the penetrometer, and the plastic limit tests, which we've just done using the sample on the glass plate.